Anasuya Lyons from Harvard, and she will talk about an important primitive. If you want to do topological quantum computation, you have to create anions, and Anasuya will explain how we do it.
Yes. Yeah, thank you for the introduction. So today I'll be talking about some protocols that we developed for creating anions and also certain types of symmetry defects via gauging in topological order. So first, I just want to say thank you to my wonderful collaborators, Leo, who is another grad student at Harvard, Nat, who is now a postdoc at Caltech, my advisor, Ashvin, and Ruben, who's new faculty at UChicago. So to begin, so sort of the context that this work lives in is the area of topological quantum computation, where we're looking to sort of leverage this concept of topological order to do quantum computation, as the name suggests. And sort of maybe the most common sort of framework for this that has also been discussed a lot at this conference is the toric code or the surface code, where we find that the sort of power of the toric code or the surface code to act as a quantum memory comes from the presence of so-called abelian anions in this phase. So the logical operators of the toric code, which have this anti-commutation relation that gives you your ground state degeneracy, really comes also from this fact that you have these non-trivial anionic quasi-particles. But these are so-called abelian anions, which means that I can really only get phases when I braid them. And this is why sort of you have to sort of add in some other modules and tools to the surface code if you want to do computation and not just memory, like information storage. But if we wanted to just sort of work with anions themselves, there is a way that we can do computation in this like topological framework by considering a generalization of anionic statistics to so-called non-abelian anions. So now I will introduce some internal Hilbert space to my anions, which I'm just going to denote here with some index, just saying that they have some additional degrees of freedom. And when I braid them, I can get something that is more non-trivial than just a phase. I can get a unitary rotation on this internal Hilbert space. And what this is showing us is that really this is a nice framework for doing computation, because immediately if we find some anions that give us some unitaries that we care about, then we can just use braiding of these anions to do computation, to do manipulation of information that we store inside of this internal Hilbert space. Okay, so that's sort of maybe the broad motivation, but specifically why do we want to sort of study these things in more detail? Well, why now? So personally, I think it's very exciting because these non-abelian phases and non-abelian excitations are becoming more and more accessible experimentally in near-term quantum devices. So as some examples, here are several experimental papers which have come out in the past year or so, which either prepare non-abelian order or sort of create and control non-abelian excitations inside of an abelian topological order. And as I explained, such phases and excitations can be used for theoretically fault-tolerant, topologically protected computing. And so if we want to do this, we need to really understand these excitations well, because we need to have fine control over them to be able to do the computation that we would like to. And then also, I think it's quite wide open to, this is a very rich field of non-abelian topological order. And there's a lot of conceptual insight that I think is still to be gained by studying these things in more detail. Okay, so overall, the goal is going to be to better understand how to control non-abelian anions in a particular class of non-abelian phases with a view towards doing some practical computation on a quantum device. Okay, so first, just basic, how would we actually create a non-abelian anion? So in a abelian phase, like the toric code, we know how to create anions. It's with string operators, like the logical operators of your code. And these are easy, right? They're just, in the toric code, they're just tensor products of some Pauli operators. And in general, for an abelian enneon, it's just going to be something finite depth. I just have to do a finite depth circuit. But for non-abelian enneons, because I have this internal Hilbert space, which means that there's information that I can store in this enneon, there's actually bounds on how quickly I can move it unitarily. So if I want to move an enneon with some unitary circuit, it was actually proven by Bowen in 2019 that any unitary circuit you would want to use to create some non-abelian enneon separated by some distance has to be linear depth in that distance. And you just think this is for some, intuitively this is due to some causality bounds. And to give you some sense of like what this circuit looks like, this is a diagram in Kitayev's original paper on this quantum double models, these generalized toric codes for finite groups. And this is what creating a pair of excitations sort of looks like on the lattice. So we can see that as this thing gets longer, things get complicated. Okay, so yeah, so just to summarize the state of knowledge about non-abelian enneons, in 2005, when Kitayev introduced the quantum double models, he also introduced these so-called Ruben operators, which are the generalizations of string operators for non-abelian enneons. And indeed, in this paper, there's this funny quote, which he says, "I do not know how to deduce an expression for such operators. I will just give an answer and explain why it is correct." So I think this really highlights how these non-abelian enneons are sort of, like no one really understands them. I think there's space to understand them better because up till now, I think we can show that some things create the enneons we want, but understanding why they do this is like a separate matter. Okay, so, and then there was some work later by Bowen that sort of exhaustively goes through the mathematical properties of these Ruben operators. And then this bound was proven that I told you about linear depth. And then more recently, there has been work actually showing that, well, you can get around this linear bound if you're willing to do some measurements and feedback. So using some non-local classical communication, you can get around this information bound. So yeah, so where does our work fit in? So sort of the two things that we would like from a Ruben formula, at least I would like, is practical feasibility. So I think that has been shown that we want some expressions that involve just 1- and 2-body gates, that the circuit is efficient where it is possible to make it efficient. And this has been shown. We also sort of show an independent way of deriving such like practical circuits for Rubens. But I think what has been missing is some conceptual clarity, some physical understanding of why these non-abelian enneon ribbons have the structure that they do. And this is what I hope I can convince you that we at least have one way of understanding. So to give you an overview of the main construction, so we're going to start with some topological order. And sort of this is a nice, I'm glad that I'm going after the previous talk because Angela gave a really nice introduction to dualities. And this is really the idea that we're going to leverage, that there is some simpler dual theory for our topological order, which if we sort of go back to use the duality in some small patch of our topological order, we understand that maybe the structure of the excitations in this simpler theory better. So we can create those. And then when we use our duality to go back, hopefully at the end of the day, we should just be left with the enneon or the defect that we want. So this is the construction. So yeah, I will go through this quickly because we've just heard a lot about dualities. I'm going to focus in particular on this duality called Kramers-Wanier duality, and in particular I'm going to focus in 2D. So the main idea is that it's some map between a trivial globally symmetric phase, which in condensed matter I might call a paramagnet, but we can just think of it as a product state. It's stabilized by just independent X operators everywhere. And there's a duality between this theory and a topological order, a gauge theory, that is it's a generalized toric code, which is long-range entangled. From a more QI perspective, we might have the following rough intuition that it's a duality between codes, where we're making some translation between the checks and redundancies of the code, and we're turning them into a new code by sort of scrambling them around. But the main idea is that we have this mapping between some more trivial, short-range entangled state and this topological long-range entangled state. So as a simple example of how this works, we can consider just the usual toric code. I'm going to start with this paramagnet, Z2 paramagnet. And the rules of the game in this Kramers-Vonnier duality, I take any X operator that I see and I turn it into this 4-body product of X's, which I can immediately identify as the toric code vertex stabilizer. And then any 2-body set of Z's like this on neighboring vertices just gets mapped to 1 Z on an edge. And the product of these 2-body Z's around any plaquette is a redundancy. It multiplies to the identity. And this generates the plaquette term of the toric code, which becomes the second type of stabilizer. So yeah, so I can think of this duality in very concrete terms as an operation that I can do to my physical degrees of freedom. I can think of it as some matrix product operator if I wanted to. And in particular, I can realize this maybe through some sequential unitary circuit, which will have to be linear depth because, again, I'm going from short range to long range entangled. Or I can do this in finite depth using some adaptive circuits, so some measurements and feedback. And the question I want to ask now is it's been well explored how this Kramers-Vonnier map maps sort of the ground states of dual theories. But what I want to highlight is that really we have an operator mapping here. And so let's consider how the simple excitations on either side of this map compare with each other. So again, going back to the simple example of the toric code, consider this 2D paramagnet that I started out with. I can create some pair of charges, which are kind of simple excitations on top of my paramagnet using Z operators. And when I push this pair of Z operators, which may be far apart, through the Kramers-Vonnier map, I get a string of Z's connecting them. And I recognize this as a string operator for a pair of E anyons. So my charges on my paramagnet become charged anyons on my toric code side. I can also think, okay, well, something else simple I can do to my paramagnet is instead of just applying the global symmetry of X everywhere that I know I have, let me just apply X in some small patch. Well, on the paramagnet, this is trivial, but if I push it through the Kramers-Vonnier map, I get just X's on the boundary. And this is a closed M anyon string, which is also sort of a stabilizer of the toric code. So I see that there's a nice mapping between charges and symmetry membranes on one side of the map and the anionic excitations of the topological order on the other. So now to talk about something non-trivial, we're going to use the same idea of sort of pushing operators from one side of the Kramers-Vonnier map through to the other to understand how we might create a non-abelian symmetry defect in an abelian order. In this case, we're going to consider the so-called Z3 or Q-trit toric code. So this is a generalization of the toric code to Q-trits, where I replace my Paulis with these clock and shift operators with the algebra that I've boxed here. And the stabilizers look very much the same, but I have to add some daggers to make sure everything commutes now. And the sort of key difference with the Z2 toric code is now I have 2 kinds of M, or flux anyons, and 2 kinds of charge anyons. And these are related by a new kind of symmetry, which is not present in the Z2, called the charge conjugation symmetry, which is sort of realized by this operator, local operator of charge conjugation, which sort of swaps the roles of the 2 anyons in the theory if I do it everywhere. Now, I can create a closed charge conjugation defect in my system by applying the symmetry just in a finite region. So what does this do? Well, if I start out with some E anyon pair, then when I cross this dotted line, an E squared becomes an E and an E becomes an E squared. But if I cross it a second time, then everything goes back to normal. So this sort of isn't really doing anything very non-trivial. It's sort of just a change of convention in some region. But if I imagine breaking this defect, closed defect line, I can have something interesting happen. So I cross the defect line, but if I cross all the way around the other side, there's no, other boundary. So my E anyon never gets back to itself. So I am left with a single anion. And I've done nothing sort of topologically non-trivial, so I should not have a single anion just lying around in my system. But the resolution to this is that this defect must host sort of some non-abelian nature. It must have absorbed the extra anion that I'm missing, which means that it has this internal Hilbert space, which signals that it's really a non-abelian defect. So how can I actually create such a thing? It's easy to create the closed one by doing some bulk operation of charge conjugation, but creating an open line, that seems difficult to do. So we're going to use duality to do this. So we note that the Z3 paramagnet has the same charge conjugation symmetry as the Z3 toric code. So which is just represented mathematically here by the fact that if I apply product of charge conjugation on one side of Kramers-Vannier, it's the same as applying it on the other side. But this charge conjugation sort of acts trivially on this paramagnet because you can think the paramagnet is just a product state of the symmetric state in the Q-trit space, and charge conjugation acts trivially on this. So what we can do is sort of push the truncated membrane, this charge conjugation membrane on the toric code, back through the Kramers-Vannier map onto the paramagnet. And what will happen is I'm going to leave this sort of trace behind this set of red controls, where the control is acting on the paramagnet, and the control is the paramagnet degrees of freedom, and the action of the gate is on my toric code degrees of freedom. And the charge conjugation operators in the bulk disappear because I've moved them onto the paramagnet, where they act trivially. So now I have some boundary action which is equivalent to sort of Kramers-Vannier and then doing this, creating this closed charge conjugation defect. But it's a mixed action between my paramagnet degrees of freedom and my toric code degrees of freedom. So I have this boundary circuit, and I could imagine just creating an open line by just cutting this boundary circuit. But I need to access sort of the degrees of freedom on both sides of the Kramers-Vannier map. This is a duality mapping, right? So I'm envisioning that I start with a paramagnet, and then I apply this duality mapping to all my degrees of freedom, and it transforms me into the toric code. So I don't really have simultaneous access to the degrees of freedom. They're really the same degrees of freedom. But what I can do is use this sort of unzipping. So what I do is just on the small patch of degrees of freedom that I need to act as my controls, I go use the duality transformation to go back to the paramagnet state. And then sort of this mixed action, these mixed gates have some meaning because I have paramagnetic and toric code degrees of freedom sort of simultaneously in my system. So this works for, we show in the paper, I won't go into detail, that this sort of construction works for generic toric codes for like defined for finite groups. We can derive the known Ruben operators for anions in these theories. And we can also derive sort of new expressions for these symmetry defects, which correspond to symmetries at the sort of group level, meaning that these are automorphisms of the group that I'm defining, that's sort of defining my local Hilbert space of my theory. Yeah, so and then just to sort of recap the main construction, I'm sort of leveraging duality to go back to something simpler inside of my topological order, and then I create a precursor excitation inside, or maybe I do something finite depth that sort of acts between my simpler degrees of freedom and my topological degrees of freedom, and then I sort of I rezip so that I'm left with my topological degrees of freedom everywhere. Yeah, and then so this is really the conceptual framework that I would like to advocate for in understanding where the structure of non-abelian ribbons come from. And indeed, we can show that sort of the original ribbons that Kitaev wrote down in his original paper, if you write them in a circuit form, you can actually do some rearranging and find that they exactly have this structure, where you first have to do some step, which looks like this unzipping, and then you do something finite depth based on the simpler phase that you've gone back to, and then you do some rezipping. So yeah, so this is sort of really, I would say, the underlying structure of these ribbon operators. And then just as a comment on the sort of practicality side of things, this also gives a nice way of understanding when you can have efficient circuits for non-abelian ribbons, because really the bound on depth is coming from this ungaging and gaging procedure. Because if you want to do this unitarily, this gaging and ungaging has to be linear depth. But it was shown recently in a series of work by my collaborators that if you are trying to do this duality for abelian symmetries or solvable non-abelian symmetries, then you can make this gaging, or by gaging I just mean this duality transformation, finite depth, if you include measurements and feedback. So we can immediately see then that if you have some solvable anion theory, then you should be able to make all of the circuits for creating symmetry defects and anion ribbons inside this theory finite depth. And one particular case to point out is that this S3 quantum double model, the generalization of the toric code to the symmetric group on 3 elements, is an example of a solvable group. And it's also universal for quantum computation. So that means that this sort of universal top model can also be sort of all of the gates inside this could theoretically be made very efficient this way. Yeah, and then just another plug for some experimental realizations to really show that these are practical circuits. Along with some collaborators at Quantinium, we used this construction to write down circuits for the symmetry defect, this charge conjugation defect I told you about in Qtrit toric code, to actually create these defects and manipulate them on their trapped ion device. We also created another type of symmetry defect in this Qtrit toric code, which is the EM duality defect, which actually behaves like a parafermion, which is kind of cool. Yeah, so just as some outlook, we have this generic recipe for writing down excitation operators for anions and symmetry defects in quantum doubles. I should say I didn't mention it for sake of time, but we also can extend this to twisted quantum doubles. And sort of natural question to ask is, can you extend this beyond the quantum double paradigm to string nets to generic topological order? There's also the application maybe beyond 2D codes, and maybe these more exotic symmetries. So I just mentioned symmetries that act at the level of the group describing your quantum double. But the EM duality symmetry, for instance, is an example of a qualitatively different kind of symmetry where it's at the level of the anion theory. So you're permuting, it's some symmetry that you realize by permuting anions. Of course, there's many other dualities that you might think you could slot into this construction to create something useful. And then sort of thinking in the more computational side of things, if we can make these circuits efficient, can we also make them fault tolerant so that we could really realize a universal and efficient and fault tolerant scheme for universal computing with these non-abelian topological orders. Yeah, so that's all I have, and thank you very much for staying to the last talk of the conference.
Okay, thank you for a nice talk. So, like by using your method you propose, like can you create all the types of anions in the S3 quantum double?
Yes, yes.
So for example, like when you think about like the charge conjugation symmetry, so basically the anion line you create are the d anions, right? to the Z2 magnetic flux. But consider like if you want to like create like the F anions, like which is the Z3 symmetry flux.
Yeah.
So can you like briefly describe like what
Yeah.
happened here?
Yeah, definitely. I think actually, in a funny coincidence, the F anion circuit is right here.
Oh, I see.
So yeah, so the idea is that actually so S3 is right. It's sort of, you can get it from this Q-trit-Tora code by gauging the charge conjugation symmetry, which means that the anions of the Q-trit-Tora code sort of become some of the non-abelian anions of S3. Which means that you kind of have an easier job with the F anion because you only really have to go back to the Z3 toric code where it is an abelian anion, and then you can move it.
Yeah, but like the point is like the charge conjugation symmetry, the Z2 symmetry, like in the Z3 toric code.
Yeah.
So like after gauging, I think the symmetry defect should correspond to some Z2 non-abelian anions and which are D anions, right?
Oh yes, yes. Oh sorry, yeah. So you can also do those. I mean, those are just. I can use this ribbon for the charge conjugation defect and just add on the step that is like ungauging from S3 to Z3. And then I just do the defect ribbon in Z3. Yeah.
Okay, yeah, we can chat. Yeah, we can chat later.
Yeah.
Sorry, could you give a few more comments on how do you extend this framework beyond 2D? Because it seems like this duality sort of just works for going from between toric code and yours.
Oh yeah. So I guess for the interest of giving an explicit example, I sort of gave I maybe made it seem like it's more of a specific thing than it is. I can define it I can define it in 1D. I can define it in higher dimensions. It's just so if you can use the generalization of this Kramers-Vonnier mapping in higher dimensions to do this sort of construction.
Do you have a notion of how to do this for some kind of non-local graph as well, or is this something that just applies
that's
to...
a really good question. This Kramers-Vonnier thing was originally sort of in the context of statistical mechanics. So it's essentially basically, if I have some statistical mechanics model, if I look at the high temperature expansion of its partition function and consider that as the low temperature expansion of some other model, the duality between these two models is the Kramers-Vonnier duality. So I can envision doing such an expansion for a generic graph, like, I just define some partition function on this graph, but but I haven't tried to work that out very explicitly.
Hi. So by symmetry defect, you mean the kind of thing that bumping used to call twists, is it right?
Yeah,
like
certainly.
Generalization or whatever, that, like similar to that kind of thing.
Yeah, I guess I mean anything which is not a deconfined anion of the theory. Because this charge conjugation defect, for instance, leaves like a line when I separate it.
So are you putting both the ribbon operator of the intrinsic non-abelian topological order and the kind of non-abelian topological order supported inside the abelian topological order on the same footing in this work, or no?
Yeah, I would say so. Yeah, I would say this sort of encompasses. I can do this for an abelian topological order for the anions too. It's just sort of it's sort of a roundabout way of deriving string operators. But yeah, certainly I think it works. It puts symmetry defects like in abelian phases and like non-abelian anions on the same footing.
Mm-hmm. So symmetry defect, you're saying that it's the kind where the two ends is in the between. There's actually a non-trivial domain wall. You're saying that?
It doesn't necessarily need to be like a domain wall in the sense, but it's something where if I there's a line where if I cross it, I implement some transformation on my system.
Right. Yeah, the more generalized excitations, right? Anyway, it's a cool work. Thank you so much.
Yeah. Thank you.
Yeah. So after you unzip, in the case of the ribbon operator, you don't see much. I mean, except for the endpoints, or.
Yeah, so the ribbon operators are, they have a structure such that they commute with all of your Hamiltonian in the bulk of the ribbon, and they only create excitations at the ends. Whereas the defect is actually modifying the Hamiltonian along the length of the string that connects the two endpoints. Yeah.
Well, it means when you gauge and engage, when you zip, unzip and zip,
Yeah.
the one of them will leave like no trace in the middle, and the other one will leave some trace in the.
Yeah,
Like,
yeah.
Okay, cool.
Yeah.
Thanks. Yeah.
Very nicely for these, you use from these lattice models, right? Topological lattice models. If you have a like a physical system, like a quantum Hall system or something, would the same scheme also work, or
I think so. I mean,
how would you do it there?
yeah. I guess here the lattice model is very useful for actually finding the circuit. Yeah. I think the philosophy of the approach will work in something like a quantum Hall system, but yeah, whether it's useful for getting any. Yeah. I haven't thought about it deeply, but I think it's certainly interesting. Yeah.
Okay, cool. So let's thank Anasuya again for a great talk.
Thank you.
Technical staff for the session. And then, yeah, thank you all for coming to North Carolina, and have a safe trip home. See you again soon, hopefully.